All right, so a kind of continuation from last time's lecture, we talked about different proteases and where they cut. We talked about trypsin, elastase, chymotrypsin, and the chemical cyanogen bromide. We're going to kind of continue that, but with a little bit of an exercise, and this is a peptide mapping exercise. So on the next few slides, or in the next few minutes, I'm going to be going over the sort of question that you could expect from this, this material. So any sort of peptide mapping problem will naturally be associated with some piece of information and some data that you'll be provided with. Okay, so this question reads, a sample of an unknown peptide was divided into several small aliquots. One aliquot was treated with trypsin, one with cyanogen bromide, one with chymotrypsin, and one with elastase. Determine the sequence of the peptide from the following information. Okay, so what that means is you had a sample that you divided. One fraction goes to be cut with trypsin, one chymotrypsin, one elastase, and one cyanogen bromide. Now, in addition to that question, here is our data. So here's our trypsin data, here's our chymotrypsin data, our elastase data, and finally our cyanogen bromide data. Now let's see what we can get done based on what we know. First and foremost, we know that trypsin is going to cut after what type of amino acid? After positively charged residues. So our trypsin data shows a dipeptide, tripeptide, and a hexapeptide. Now, when you see something in parentheses like this, this shows you that the exact sequence is not known. However, it is known that this dipeptide consists of arginine and serine. This tripeptide consists of tyrosine, methionine, and threonine. And then finally, our hexapeptide consists of those amino acids. In the order, we don't necessarily know. However, we can deduce some things about this. First and foremost, when we're looking at our dipeptide, well, we know that trypsin is going to cut after a positively charged residue. Between these two amino acids, you have arginine and serine. Now, being in parentheses, we don't know the exact sequence. However, we basically have one of two different options. Now, we ultimately, however, only have one option. And that is this peptide, this dipeptide, is sequenced SER-ARG. How do we know that though? Well, we know that because arginine is a positively charged residue. And trypsin is going to cut whatever peptide bond exists after arginine. Okay, so what we want to do with this sort of problem is we want to dissect each of the pieces of data that we're presented with and use the knowledge that we have based on that based on that protease. Okay, so then what we have is a dipeptide, and I'm just going to draw a very crude representation of this overall peptide here, and then we have a tripeptide, 1, 2, 3 amino acids. Now, do we know if this tripeptide precedes or follows our dipeptide? We don't know. However, when we look at our tripeptide sequence, we're looking again for trypsin to cut after a positively charged residue. Now, when we look at these three different amino acids, tyrosine, methionine, and threonine, are any of those positively charged? No, they're not. Tyrosine, it can be involved in hydrogen bonding, but it has no net charge. The R group does. Methionine, nothing. Threonine, nothing. All of these can be involved in hydrogen bonding, however, the R groups themselves don't have a positive charge. So what does that mean? Well, that means that no matter how you organize this, and we don't know anything about the sequence, but no matter how you organize this, well, there isn't a positively charged residue that you're going to put at the end. Meaning that this is your C-terminal peptide. So now the question that I was asking a moment ago, do we know if our tripeptide follows the dipeptide or precedes the dipeptide? Well, we know that it cannot precede our dipeptide because there's no positively charged residue within our tripeptide. So our tripeptide has to be at the very end. So now what we're looking at is, let's expand our overall peptide. We've got a dipeptide, a hexapeptide, 4, 5, 6, and a tripeptide, 1, 2, 3. Okay, so now the one thing that we can conclude is that this tripeptide is at the C termini. So that means our C termini consist of tyrosine, methionine, or threonine. In what order, we don't necessarily know, but we know that those 3 amino acids are going to be found at the end. Okay. Now the question is, our hexapeptide and our dipeptide, is the organization of our overall peptide like this, where we have our, I'm going to call this a dipeptide, dipep, and our hexapep? Or is it a hexapep followed by a dipep followed by our tripeptide? We don't necessarily know that. So that's one of the things that we have to deduce based on all the other information that we're presented with. Now, with that said though, can we look at our hexapeptide data and deduce anything about it? And the answer is yes, we can, because again, we're looking only at our trypsin digestion information. So our trypsin digestion information, when we look at our different amino acids in our hexapeptide, tryptophan, asparagine, isoleucine, glycine, lysine, and methionine. Are any of those positively charged? Yes, lysine is positively charged. So we know that our hexapeptide has to be amino acid 1, 2, 3, 4, 5, followed by a lyse. Okay, is that our N-terminal peptide, or is our dipeptide our N-terminal peptide? From the information that we're presented with only the lysine data, we don't know. Now, I'm going to go on to the next bit and basically expand upon this and more or less show the different options that we have from our trypsin data. So hang tight. But with that said, after I've done the trypsin data, I'm going to go through chymotrypsin, elastase, and cyanogen bromide data. So I'm going to go through all of this so that we can figure out where we are. So we have our tripeptide, which I'm going to draw X's to represent those amino acids, and then I'm just going to draw an arrow to show that's where we're talking about. And we have our dipeptide that we know has a sequence of SER, ARG. Now, our hexapeptide, we don't know the exact sequence of this. However, we do know, and I can put this in parentheses, TRP, ASN, oopsies, ASN, ILE, GLY, MET, close parentheses, MET. So our overall peptide, I'm going to mark this as A and this as B. Our overall peptide could be A, B, tripeptide, or it could be B, A, tripeptide. Okay, so you have to use this information and then use additional information in conjunction with it. Okay, so this is some information that we can carry on with our future analysis. So let's go on to look at our chymotrypsin data next. Now, chymotrypsin shows us that we are going to get 2 pentapeptides. So that's 2 5 amino acid long peptides and a free methionine. Now let's rehash what we got from our trypsin data. Our trypsin data shows us that we have TYR, and I'm going to write out my tripeptide, TYR, MET, and THR on our C termini. Then we have A or B, and our A peptide, that is our SER. Actually, let me change the SER-ARG, because we know we have that positively charged residue at the end. Then we've got our hexapeptide, where we have a lysine at the end, LYS, TRP, ASN, that would be ILE, oopsies, need more space, isoleucine, glycine, and MET, LYS at the end. Okay, so it's either A or B in that sequence. Now, when we look at the data that were presented from just our chymotrypsin treatment, one of the things that I pick out from this is we're getting a free methionine. Okay, so a free methionine. We have methionine in two different groupings. We have methionine in our C-terminal peptide, and I'm going to underline it here. We've got it somewhere in our C-terminal peptide, and we've got it somewhere in our B peptide. Now, we could make some guesses. What we do know, however, with this information is that chymotrypsin is going to cut after a bulky aromatic residue. So it's going to cut after something like a tryptophan or a tyrosine or a phenylalanine. We don't have to worry about any phenylalanines being here, but it's going to cut after those. Okay, so now let's consider our options. We've got methionine in our B peptide and methionine in our C-terminal peptide. Well, if we had, let's go ahead and use this information to speculate about our C-terminal peptide. If we had this peptide arranged as THR, TYR, MET. Okay, so this is our C-terminal peptide. So this is at the very end of our peptide. If we cut with chymotrypsin after our TYR, would we get our free methionine? Yes, we would. Okay, now if we looked at our B peptide there, and keep in mind, this is a completely separate fraction. So you're getting a small fraction of this and you're cutting with chymotrypsin. So let's arrange our B peptide based on what we know from our trypsin digestion, and let's try to arrange this. So we could have a TRP, MET, okay, then it doesn't really matter about how you arrange the rest of those residues. ASN, ILE, and GLY, and then we have a LYS at the end. And then, of course, we have that C-terminal peptide. So if we cut with chymotrypsin, and we had our B peptide, if we cut our B peptide with chymotrypsin, it would cut right there. So that would get us a methionine, but would it be a free methionine? No, because that methionine is going to be followed by a lysine. So with that, we can look at our kind of two proposals here. This organization right here, where we put methionine at the C-termini of our polypeptide, or methionine somewhere in this B location, in this B peptide. Well, based on the fact that we are getting a free methionine, we have to have an aromatic residue followed by a methionine, followed by nothing. And the only way that we get that, or that we achieve that, is by placing that methionine on the C-termini of our peptide. So now what we can do with that information, and this is, keep in mind, we're only looking at our free methionine here, we can deduce a little bit more about our peptide. We know that our C-terminal peptide has to be threonine, tyrosine, and methionine, because chymotrypsin is only going to cut after an aromatic residue, and whenever it does so with a C-terminal peptide here, it's going to liberate a free methionine. Okay, so this doesn't kind of achieve or solve our overall structure for our peptide, but it gets us a little bit closer. So now what we need to do is look at our other two results. Our other two results say that we have an asparagine, a serine, a glycine, a tryptophan, and an arginine. So one thing that we can do with this is we can say, well, we know that whenever we cut with our trypsin, the serine and the arginine were back to back, SER, ARG. Okay. Then, since trypsin is it's going to cut after positively charged residues, we can look at this pentapeptide and rearrange it to say ASN, then GLY, and TRP. Okay, because this is a positively charged residue, trypsin has to cut in this specific location right here. Okay, now ASN, GLY, TRP. Chymotrypsin is going to cut our overall peptide to produce something that looks like this. When we overlay our trypsin data and our chymotrypsin data, this is what we get. When we look at our chymotrypsin data, what can we conclude? Chymotrypsin is going to cut after an aromatic residue. Is asparagine an aromatic residue? No. Is glycine an aromatic residue? No, it's not. Tryptophan is, however. So this peptide, this pentapeptide, we know from our chymotrypsin and our trypsin data, first of all, from our trypsin, it is SER ARG. Combining our trypsin and our chymotrypsin data, we know that we are going to follow that with ASN, GLY, and with our chymotrypsin data, we know that this is going to end with TRP, because TRP is an aromatic or a bulky aromatic residue, and so we have to have that organization for that pentapeptide. Okay, now with our other pentapeptide, reads threonine, methionine, lysine, isoleucine, and tyrosine. Okay, so this right here, we know at the very end of it is going to be TYR. And then it's just THR, MET, LYS, and ILE. Okay, how do we know that tyrosine is at the end? Because tyrosine is a bulky hydrophobic residue. Now, when we look at this peptide, and this is one of the ways that this gets kind of confusing. When we look at this peptide right here, the one that we just picked up, and we compare that to our data from our trypsin, well, we know that we have a sequence that is threonine followed by tyrosine. So we know that this residue right here and this residue right here are going to be at the C termini of this starred residue, or I'm sorry, of this starred polypeptide. So what we can do is take that polypeptide and rewrite it as MET, MET, comma, ILE, comma, LYS, put those in parentheses because we, at this point, don't necessarily know the sequence of them. We know that we're going to follow that with THR, TYR. Okay, so this is one of the places that this gets pretty darn confusing because you're juggling all these polypeptides and you're overlaying data from different polypeptides or different polypeptide treatments. So now what we've done is we've taken though this 11 amino acid long polypeptide and we've started to reconstruct it. So we know that at the N termini we have a serine followed by an arginine. Then we have an asparagine or a glycine followed by a tryptophan. We have another peptide that results, that's a methionine, isoleucine, or lysine, followed by a threonine and a tyrosine, followed by our free methionine. Now I said that this serine was at our N termini. How did I know that? Well, I knew that because whenever we looked back at our free methionine, right here, our free methionine, and we placed that in our C-terminal peptide that we got from our trypsin treatment, ultimately the only way that we could construct this is with, or reconstruct this is with that serine arginine dipeptide being the N-terminal peptides. So now, if we want to rewrite all of this, here's what we have. SER, ARG, asparagine, glycine, TRP, I'm sorry, I need to put these in parentheses and separate them by a comma because we don't know if it's asparagine followed by glycine or glycine followed by asparagine. After the tryptophan, we have we have a tryptophan followed by MET, ILE, LYS, followed by THR, TYR, followed by MET. Now, with this information though, let's look at this pentapeptide right here. Yeah, that pentapeptide right there. Could we figure anything else out about this? Well, one of the things that we can do is we could look at our trypsin digestion. Our trypsin digestion showed us that we would get a 6 amino acid long peptide with a lysine at the end of it. That 6 amino acid long peptide would have a tryptophan, a methionine, a isoleucine, a glycine, and an asparagine. And at the very end, we have our lysine. I'm going to switch to a different color here, because here is our lysine. So of our so-called B peptide, we have a tryptophan, an asparagine, isoleucine, glycine, methionine, and at the end, a lysine. Well, here are the 5 amino acids of those 6, and lysine has to be at the end. So we could basically remove this parentheses and now place it in like that. And we can do that because we're comparing our chymotrypsin and our trypsin data. Okay. So at this point in time, if you need to go back and watch this again, this is an exercise that does take a lot of work just because you have to figure out when you need to apply data that you received from your first digestion. You need to compare that to your second digestion and so on. So this requires quite a bit of paper whenever you're doing this sort of thing. But at the end of the day, what matters are the fundamentals. What does each enzyme cut after? Okay, so now our next enzyme is elastase. Elastase is going to cut after small amino acids like glycine and alanine. Now, this elastase treatment is going to give us this tetrapeptide and this septapeptide. But let's go ahead and reconstruct what we currently know. We know that our polypeptide is SER, ARG, GLY for glycine, followed by asparagine, ASN, followed by TRP, followed by isoleucine and methionine, followed by lysine, threonine, tryptophan, and methionine. Okay. Now, when we look at all this information, what this is going to show us is, or whenever we look at this information, I put a parentheses there and I didn't need to. When we look at this information and we compare it to our treatment with elastase, okay, elastase is going to cut after a glycine and alanine. What we need to do is we need to find those residues in this polypeptide that we've proposed. We have glycine. Do we have any alanines? No, we don't. Okay, now when we cut with elastase, which cuts after those small residues, we're going to find glycine and asparagine, serine, and arginine all in one peptide. Now when you look at that, we know from our previous data where serine and arginine fall, but we don't know if asparagine comes before glycine or glycine is after. Now, if elastase is going to cut after glycine, and we're going to have that asparagine in that peptide, asparagine has to precede it. So we know that this tetrapeptide, or this tetrapeptide, is serine, arginine, asparagine, glycine. So we can basically, from this piece of data, we can eliminate our parentheses around the glycine and asparagine because we know that asparagine precedes glycine. Now, what follows that? We don't really get any more information from this elastase treatment. Then we're left with TRP, ILE, MET, lysine, threonine, tryptophan, and methionine. Okay. Now, when we cut with cyanogen bromide, what is that going to give us? Cyanogen bromide is going to cut after small residues, or it's going to cut after methionine. Okay, so we need to find where our methionines are. Here's methionine, and cyanogen bromide would cut after that. Well, methionine being a C-terminal residue just goes to show that if you cut after that, there's no polypeptide, or there's no peptide bond to cut. Okay, so here's another methionine. It's going to cut here. So after methionine, it's either going to cut a bond between methionine and isoleucine or methionine and lysine. And so we can anticipate what our results are. If methionine is followed by lysine, we will get two products. Here is one. I'm going to underline it in red. And here is the second one. Now, in the event that methionine is followed by isoleucine, well, then we have a sequence that is ILE, lysine, I'm going to switch to single letter codes here, threonine, tryptophan, methionine. Is that what we get from our products? No, we get a tetrapeptide, which is lysine, tyrosine, methionine, and threonine. We already know that sequence. And we get a septipeptide, which is glycine, arginine, serine, asparagine, methionine, isoleucine, and tryptophan. And the only way that we can get that is if we have a polypeptide sequence that is isoleucine followed by methionine followed by lysine. So then we have our cyanogen bromide treatment right there. All right, well, this is quite a bit of work. This video is almost 30 minutes long. It will take some time to do this sort of thing. Will there be a problem like this on your exam? Absolutely. Will it be this involved? No, this is a great thought exercise though. This is a great way to work through the process. Make sure that you understand where each different protease is going to cut, because that will help you kind of remember all your fundamentals. At the end of the day, this is a lot like a logic puzzle, or this is a logic puzzle. You're finding relationships between different pieces of data, and basically you're reconstructing something. So this is a great critical thinking exercise, and I think these are fantastic problems because they nail down the concepts and they, kind of assure that you know what to expect. All right. Well, thank you very much for watching. I hope this was helpful. Have a great afternoon. Bye.